So the final step is gain margin in dB. So GMdB is equal to minus 20 log MPC, that is minus 20 log 1.66. So it is going to be minus 4.4 dB. So gain margin in dB for the open loop transfer function given is minus 4.4 dB. Similarly, we can also find out the phase margin. And to find the phase margin, we have to calculate first what will be the gain crossover frequency. Now, we know how to find gain crossover frequency. Equate the magnitude to 1. So what is the magnitude here? 10 by omega into 1 plus omega square into 4 plus omega square, that is equal to 1. So then you simplify it, then we can take that x is equal to omega square, then I can write out in terms of the x, then you will be if you simplify, you will be getting the equation x cube plus 5x square plus 4x minus 100 is equal to 0. So if you simplify this equation, I mean if you find the solution of this equation, you will be getting x is equal to 3.24, and also I have complex number. You can ignore the complex number, I can take x is equal to 3.24 and x is nothing but omega square, then you can write what will be the omega. So it is going to be 1.8. So omega GC is 1.8. Once you have omega GC, I can substitute the omega GC in phase angle expression to get the phi GC, which is the second step in the phase margin. So phi is already known to you, minus 90 minus tan inverse omega minus tan inverse omega by 2. In place of omega, substitute omega GC, then you substitute, then you will be getting the phi GC as minus 192.9. So the last step in the phase margin is equal to 180 plus phi GC. Phi GC is minus 192.93, so phase margin is going to be minus 12.93. So this way you can find out the phase margin. Now look at the summary of it. When you look at the summary, I have omega PC is root 2 and the gain margin is minus 4.4 and the omega GC is 1.8 and phase margin is minus 12.93. So phase margin is negative, gain margin is negative, therefore my closed loop system is unstable. So I can directly say with this result, closed loop system is unstable. Similarly, we look at another problem. The problem statement goes like this. Find the gain margin and phase margin of the system whose open loop transfer function is given by GH of S is equal to root 2 divided by S into S plus 2 and investigate the stability of the system. So the problem statement again, it is similar to the last one where the open loop transfer function is given and we need to find gain margin and phase margin. So GH of is available, root 2 by S into S plus 2, then S is equal to j omega, GH of j omega is root 2 is already there, denominator j omega plus we have S plus 2, therefore 2 plus j omega. The magnitude is numerator is same, m is equal to root 2 divided by j omega, so we will be getting omega under root S plus 2, therefore you have omega square plus 4. Or 4 plus omega square. This is a magnitude expression. What is the phase angle? Numerator I have constant 0, denominator j omega minus 90 and I have S plus 2. So you will be getting minus tan inverse of omega by 2. So phase angle I can write it as minus 90 minus tan inverse of omega by 2. So magnitude and phase angles are available. See steps to be followed to find the gain margin. To find the gain margin, equate the phase angle to minus 180 degrees so that I will be getting omega PC. So minus 90 minus tan inverse omega by 2 is minus 180. So I can cancel all minus. So you will be getting 90 plus tan inverse omega by 2 is 180. I can take 90 other side. So tan inverse omega by 2 is 90. Then you apply tan here, you will be getting infinity here and here it is omega. So what will be the omega? Omega is infinity, which means omega PC is infinity. So this particular problem, omega PC we are getting infinity. What is the meaning of it? Omega PC infinity. So which means the phase angle equation is going to be minus 180 at when the frequency is infinity, which is the phase crossover frequency. When you relate this with the phase plot in the bode diagram is having in between minus 90 and minus 180, which means the phase plot is not crossing minus 180 degrees line. When phase plot is not crossing minus 180 degree line, then we can take that omega PC is infinity. Then what I need to do to find the gain margin? So we need to substitute this in the magnitude expression. What will be the magnitude? Root 2 by omega into 4 plus omega square, means omega PC is infinity. So what will be that corresponding magnitude? That is MPC. So MPC you are getting 0 and gain margin is infinity. So we are getting gain margin is infinity, which means my system is absolutely stable system. Whatever may be the K value, all my closed loop poles lie in the left half of the S-plane. When all the poles in the left of the S-plane, my closed loop system is always stable irrespective of the gain value. This is the result of the gain margin. We have omega PC infinity, gain margin also infinity. But we can find out what will be the phase margin. To find the phase margin, find out what is the gain crossover frequency, which means equate the magnitude to 1. Magnitude is root 2 by omega into square root of, we have 4 plus omega square is 1. Then you simplify this, again you take x square is equal to omega square in terms of x, you will be getting. Then after that you can find the solution of x, you will be getting a positive value and negative value. We are taking only positive value, that is 0.45. When you find under root of that, that will be, you have 0.67. So omega GC is 0.67 and substitute this in the phase expression. The phase expression is, phase angle is minus 90 minus tan inverse omega by 2. In place of omega, substitute omega GC. Then you will be getting the phi GC value, that is around minus 108.52. So phi GC available. Phase margin is very simple. Phase margin is 180 plus phi GC. Then if you do that, you will be getting phase margin around 71.5 degrees. Now in this case, gain margin is infinity, phase margin is positive value, therefore the system is a stable system. As I said, gain margin is infinity, then I can say system is absolutely stable system. The closed loop system is going to be absolutely stable.